We talked about a differential equation, and a differential equation is where you have x, y with the derivative of y, or maybe the second derivative of y. So in this exploration, it says, let's look at the differential equation given by dy dx equals 2x. And if I were to look at every single point on a graph, what does the dy dx represent? It's the slope, okay? Good job. All right. It is the slope of the line tangent to y at that particular x value. So what's interesting is we are going to develop something called a slope field. So using the differential equation above, I like to call these toothpick tangents because we're going to be taking because we're going to do these in a bunch of spots, we're going to draw not long tangent lines, but teeny tiny little ones. We call them toothpick tangents. So I'm going to get you started, then pause and let you try to finish these. So if I have the point -2, 2, and I have dy dx equals 2x. So if I want this slope, isn't that just 2 times -2 or -4? Now, since there's no y in that differential equation, do you see there's no y? It's just dy dx equals 2x. I don't even need to look at the y values. Wouldn't this be -4, -4? And then this one is 2 times -1. So it's -2, -2, -2. All right, let me give you a brief head start on me and go ahead and fill in the rest of the table. So you should get 0, 0, 0, 2, 2, 2, 4, 4, 4. Okay? So for each of the ordered pairs above, we're going to sketch a mini toothpick tangent at that point with the given slope. So I'm going to do a few of these and then see if you can I look for patterns. And one of the patterns is where x is -2, they're all a slope of -4. But I also like to start with my easy ones. So if I go to 0, 1, that has a slope of 0. 0, -1 had a slope of 0. 0, 0 has a slope of 0. So this is what I mean by a toothpick tangent. It's just a small little dash. Then at 1, 1, we have 2. So it's positive, and so I like to think of it like that. And nobody's looking for perfection, okay? Nobody's looking for perfection. But I like to think of if I had 1, it's at a 45-degree angle, right? If I have 1, so 2 is going to be a little bit steeper, okay? And again, not perfection, but if it's greater than 1, it needs to look greater than 1. And then at 1, 2, it's the same. And 1, -2. So do you see, whoops, it's a little bit off. Wouldn't that entire column be the same, even though I only gave you 3 of those points? So this is what it means is, can you fill in the rest of the points based on the pattern? So all of these should be 2. And shouldn't all of these be 0? Then at 2, 1, it was 4. So I just need that one to look steeper than the one beside it. Now let's go on the other side. My -1, 2, this is -2, so I kind of think about what would -1 look like and then make it a little bit steeper. Then because of the differential equation, dy dx equals 2x, I know that where x is -1, this whole column is the same. So then let's go to the -2, 0. So that one's negative, but a little bit steeper. Now, even though we were not asked in the table, can we figure out what's going to happen when x is 3? I actually could figure out what's the slope. What would it be? 6. And then we can sketch it. It just needs to be a little bit steeper than the 4. And then over here, this one's going to be -6. Okay, then what's kind of cool, once you sort of get the hang of this is, and what was created, which I haven't defined yet, is a slope field, is dy dx equals 2x. Now let's stop and think here a minute before we make our little sketch. If I have my derivative is 2x, what do you do to undo a derivative to get to y? Integral. Okay, we're going to integrate it. So if I integrated 2x, what would that be? X squared. Now, it's actually x squared plus c, right? Because I don't have a particular point here. But x squared is what shape? It's a parabola, right? So I could get it to go through here. I could get it to go through here. Do you see that? How many curves are possible? Infinitely many, okay? So there's infinitely many curves because the same curve could be shifted up or down. So this is what we refer to, this is a slope field. And a slope field shows the family of solution curves. So we just talked about this. It said in number 5, find a general rule for y based on your knowledge. So if I did the antiderivative or integral of 2x, this would be x squared plus c. So yes, the curve is a parabola. And the plus c represents different possible y-intercepts. So this is really, really neat because this really does kind of sew together what we were doing in the previous unit, in that this is why you have a plus C, that there are infinitely many possibilities unless we have more information. So, in a later lesson, we will learn ways to solve a differential equation analytically. However, doing so can be difficult or sometimes impossible. A graphical approach to solve a differential equation is by creating slope fields, which show the general shape of all solutions to a differential equation. So if you consider a differential equation, y prime equals f of x comma y, that's in terms of x and y, for every point xy in its domain, y prime determines the slope of the solution function at that point. If you draw a short line segment with the slope indicated at each point on y prime, the slope field will show the general shape of all the solution functions to that differential equation. So let's look at example 1. If I have the differential equation dy dx equals negative x over 2y, and we want to sketch the slope field. All right, I do tend to do these in my head, but we'll write some of them out. Do you notice that y cannot be 0, correct? So I want you to think about, on a coordinate grid, where is y equals 0? It's the x-axis. Okay, so what's going to happen, since y cannot be 0, we're going to put nothing, no little toothpick tangent lines on the x-axis because it's not defined there, okay? So then let's just start picking some points. If I do, well, what would happen for all of the x zeros? It would be 0. So I could do that whole row, but not doing on the x-axis. So do you see how sometimes you can just start with 1 and go, oh, okay, that's all the same. All right, so then I got that whole column. Let's look at 1 comma 1. This would be negative 1 over 2. So if I go to 1 comma 1, so I think about where negative 1 is, and then that's a little bit flatter. All right, let's do 1 comma 2. That would be negative 1/4. So that's even flatter. Then let's do 1 negative 1. So that's negative 1 over negative 2. Oh, so do you see this is going to flip and be positive 1/2. And then if I do 1 negative 2, that's negative 1 over negative 4. So that's still positive but flatter. So I'm going to pause a moment, and I want to give you a minute or two head start on me, and I want you to try to fill in your other dots. You can either do them mentally, or you can write them out. And if you're a fast worker, see if you can tell what shape this slope field looks like it's creating when you're done. Okay, so what shape looks like it's emerging? A circle, doesn't it? I'm seeing something that's going to look like, that's not a great sketch, but it's looking like it's going to be a circle. So let's look at example 2. They do sometimes ask you, yeah, okay.
Would you have like vertical lines on the x-axis because it's undefined there?
No, you actually can't, and that's been a discussion on that AP discussion board. Is undefined, and so you're not supposed to put anything at all there.
Even though a vertical line would be undefined.
A vertical is undefined.
But it's undefined for
different reasons. Okay. Yeah, so we don't know like why it's undefined. Yeah, that's a great question. All right, so I have seen on some of the free response where it has you do, and it's usually not more than the 2 by 2 that they ask you to do, but more often than not, it's a multiple choice question. So example 2 says, shown to the right is a slope field for which of the following differential equations. So I'm going to pause a moment, and I want to see if you can figure out which this would be. And there's lots of correct ways to figure this out. If you need a little help, I pick a point somewhere and go try it in the answers, A, B, C, D, and see which ones give me that. And if more than one gives me that, then I got to pick another point and then eliminate out of that. All right, discuss at your table what letter choice and like why. Why is that working?
Y is greater than 1 greater than x. One is 1 and then 1 x is 1 greater than y.
All right, the correct answer is C. Does somebody want to explain how you thought of it? Yeah.
So when x equals y and slope equals 0, so I knew that they had to be opposites at some point. And then so I checked the points. I guess that eliminated A and B.
Yes, okay.
And then I checked the point x equals 2 and y equals 0.
Okay.
So I saw that positive 2 minus 0 doesn't equal negative, so
Awesome. That's awesome. Okay. Excellent. I did something similar in that I checked 6, 6. I just picked a random point, and that immediately eliminated A and D. Both of these gave me my slope, or dy dx was 0, and then you have to pick another location. So awesome. That's an awesome way to work that. All right, this next example, it says the graph to the right shows a slope field for the function y equals f of x. Now, I want you to key in on the word function. in order to have a function, remember it's got to pass the vertical line test. So there's a little bit of Algebra 1 sneaking in here. So we can only draw one possible solution here. So if I have 0, 6, because it's a function, I can't draw the piece underneath. Does that make sense? That's why I can't have another piece there. So our specific solution curve must pass through 0, 6. So then what would be the range? Well, this looks like this y equals 4 looks like some kind of a asymptote. So I'm going to put the range is 4 to 6. But keying in on the word function. Oh, no, sorry. Yeah, sorry. Yeah, it wouldn't go past 6. It starts at 6. Because it's x, yeah, thank you, greater than or equal to 0. No, because x is greater than or equal to 0, so that's to the right. Yeah, that's to the right. All right, let's look at example 4. This is like example 2. Now that I showed you how you could do that, this one's just a little different. It says, what is the general solution to the differential equation that generated the slope field to the right? You have lots and lots of options here. Yep, I'm hearing some good answers there. It is letter E. It is going through that origin. Now, it can have shifts, and that's what the plus C will do. All right, last example. Consider the differential equation dy dx equals x squared times the quantity y minus 1. Describe all points in the xy plane for which the slopes are positive. So stop and think a moment. They have to be positive. Good question. Is 0 positive? No, 0 is not positive. All right, this is what I heard you were saying. So for dy dx to be positive, you need x squared times the quantity y minus 1 has to be positive. X squared's positive all the time except when x is 0. and y minus 1 is positive when y is greater than 1. So the points where x does not equal 0 and y is greater than 1 will yield slopes that are positive.